Hello everyone and welcome back to our class in financial risk management. We've talked about the binomial model for option pricing in the last week, and we will now discuss the trinomial model, which is simply an extension of the binomial model with the difference that the underlying can now take up to 3 different values. It can go up, it can go down, or the underlying price can stay the same. So it's a very natural extension of the binomial model. And we'll again have a look at the stochastic process of the log prices, LNST. And as I said, where's my cursor here? Okay. The underlying prices can now take up 3 new values. So we have 3 risk-neutral probabilities: up, down, and middle, PU, PM, PD. And again, more theoretically, we are trying to approximate the underlying diffusion process, the underlying continuous stochastic process, by using a discrete one. So the process, which is the difference in the log prices, is again assumed to be a diffusion process with a parameter nu in the drift and a volatility parameter in the diffusion component. We assume that nu is given by r minus sigma squared half, and we now have to make assumptions. We've seen this in the binomial model, that we have to make assumptions so that actually the continuous process and the discrete process, they are equal when it comes to certain moments. For example, when it comes to the expectation and the volatility. Same here, we assume that actually the expected value of our discrete approximation is nu delta t, which is the expected value of expectation here in the continuous one, so on, and same here. And actually, we now require the 3 probabilities to add up to 1, which we didn't need in the first scenario of the binomial model, but now the 3 probabilities need to add up to 1. We get a system of equation. Actually, you don't need to remember this. You need a little bit of calculations to finally come up with these 3 probabilities. We can then select this parameter delta LNS, and actually it's more interesting to see how this works in Matlab, how this works in practice. We have a European plain vanilla call again. Remember that under Black's codes we do know the theoretical price, at least analytically, and we have the current stock price equaling the strike is equal to 100. The interest rate is assumed to be 6%, maturity is 1, volatility 60%, and we assume delta LNS is 0.2, and we can get the 3 probabilities from our model, and we want to implement this in Matlab. This function is called trinomial. Again, we need those parameters as input. We want to make this Matlab program as efficient as possible, so we pre-compute those quantities that remain invariant throughout the calculations, and these invariant quantities are delta n, nu, the discount factor, and the 3 probabilities pu, pm, pd. We already discount them because later on we need to take the payoffs of the underlying, and we have to weight them using the probabilities, but we also need to discount those expected payoffs, so we can already multiply the discount factor into the probabilities. We set up the starting values in lines 11, 12, 13, and 14 of the underlying, and then we set up the lattice. We start from left to right, calculate all the potential underlying values from left to right. Then we take the last column, and we know the ultimate payoffs in all potential outcomes of the underlying. And then again we take the discount factor, discount all those potential payoffs, and go back from right to left to calculate today's price of the option. These are just the three for loops we need, actually 2 for loops we need to calculate the underlying prices and then to calculate the option prices. And if we now do this, you can see that actually if we calculate this, for example, with delta LNS of 20%, we get a price of 14.64. Actually, the true Black-Scholes price, if you were to consider this the true price, the Black-Scholes price is 14.71. If you use a slightly different parameter, you can see that it changes a little bit around 14.3, 14.4, but it's close to the Black-Scholes price. And this is how it works. Actually, we have the underlying price and we go, these are the option prices, but you take the underlying, it starts out at 100, then you go right to this column, then you have the different underlying prices, you calculate the payouts from the option, and then as before with the binomial model, you go from right to left, back, and you get the option price, which in this case is 14.64. So it's basically the same, and by changing the number of iterations, or not iterations, but the number of intervals you want to divide your remaining maturity of the option into, you get the option price. Okay, so this is the binomial and the trinomial model. We'll continue now with Monte Carlo simulations, which is even simpler actually. This is even simpler. It's a common technique for pricing options, but it's actually very, very simple, and we'll show this in Matlab. You can read about this again in the Brandy Mate book. It's usually included in almost all textbooks on risk management and even in banking. However, in many German textbooks, I would say these German textbooks really don't get it, and they don't get the main idea of Monte Carlo simulation. What you will find in many German textbooks is that they will say, well, you can price an option using Monte Carlo simulation or Black-Scholes or Finite Differences or the Binomial Model. Yes, theoretically you can, but in practice you will never do both, and you will never use Monte Carlo simulation if you can do Black-Scholes. We've seen from the derivation of the model that the appealing property of the Black-Scholes-Merton model is that it can be applied to any derivative. It's extremely general in the sense that it gives you the price of something which has a price that is a function in the underlying, just a function. We don't know which function. But for plain vanilla options, we do know the analytical pricing formula from the Black-Scholes-Merton model. Then you don't need all these methods like the binomial model, the trinomial model, Monte Carlo simulation, finite differences. But as soon as you have an exotic option, a more complicated option with a more complicated payout profile, so that Black-Scholes doesn't have an analytical solution, you need to find another method. And this is when you can resort to Monte Carlo simulation, because in the end it's a brute force approach where you use computer power to price the option. So keep this in mind. In many German textbooks you will find statements like you can use either Black-Scholes or Monte Carlo simulation. Yes, you can, of course, but why should you? Why should you use Black-Scholes? No, why should you use Monte Carlo simulation if you can use Black-Scholes? And we will see that in the end, if you do have the Black-Scholes model and the Black-Scholes analytical pricing formula at hand, Monte Carlo simulation will probably, if you do your thing right, Monte Carlo simulation results will converge to the Black-Scholes result you already have on hand. So again, why do we need Monte Carlo methods in option valuation? All these methods, like for example lattice models like binomial, trinomial, they are suitable for pricing simple, plain vanilla options. Yeah? As long as the payoff profile of the option is not too complex. If it's a plain vanilla option, you can already probably use the analytical pricing formula from the Black-Scholes model. Now, the advantage of lattice methods over Monte Carlo methods is that they require less computational effort. On the other hand, Monte Carlo simulation uses computer power, brute force, and simply simulates and then prices the option based on those simulations. This is particularly convenient in the case of so-called path-dependent options. What are path-dependent options? These are exotic options whose payment at option maturity depends not only on the final price of the underlying at maturity, but also on the time evolution of the price. So, for example, we've seen many options for which, if this was the underlying, we only took this final value. But actually, if you take now, for example, the minimum, or the maximum, or the average of the price, and compute the option payout based on this time evolution of the underlying price, then it's what we call a path-dependent option. One simple example is an arithmetic Asian option. It's a path-dependent option, and as you can see, it pays out the maximum of 0 or the maximum of 0 and the average stock price in between. Now, for plain vanilla option, we've seen only the payout at the stock price, the underlying price at the very end is relevant. For this path-dependent option, it's the average. So we need to know all the stock prices in between. And then Black-Scholes Merton model can be applied, but it cannot be solved. As you might remember, Black-Scholes yields us a stochastic partial differential equation, and this SPDE cannot be solved for this type of option. And if it gets more complicated, again, the partial differential equation cannot be solved. So what do we need? We need to simulate from the underlying, and we need to simulate from the assumed stochastic process for the underlying price. So we again consider our diffusion process. The change in the stock price is given by drift times dt plus drift times dt plus diffusion times dwt. The simplest way of discretizing this is a continuous process. We want to discretize this so that we can simulate. The simplest idea would be the so-called Euler Scheme, which assumes that the change in the stock price, DST, so we are here, let's say we are here, and we want to know, does it go up, does it go down, does it go up like this, does it go down like this, where is our stock price going? So this is delta ST. Does it go up, does it go down, and by how much? The idea would be, okay, this is ST plus delta T minus ST, the current stock price. And we could say, okay, let's discretize this by saying drift, that's a parameter, times change in time. We would say this is 1 day. So we would simply assume this is 1, plus diffusion parameter, square root of delta T is again 1, times epsilon, and epsilon is a standard normal distribution. So what we would do is, let me just mark this. This is, sorry, I need this here. This is known. Parameter is known. This is known. This is delta S. We do know the parameter here, B. We do know the square root of delta T. And the only thing that needs to be simulated is now epsilon. Let's simulate epsilon, and we simulate from the standard normal distribution, could be maybe 0.2, and then enter 0.2 into this equation, and you have the first simulation. So 20% here, 0.2, is a random number that is simulated, and we insert this into the equation, and we get the first simulation. Problem is that this discretization leads to a discretization error. The Euler scheme is not the best. So what we are doing is we start with the geometric Brownian motion for the log prices. So we can see that this is the equation, the defining equation for the geometric Brownian motion for our log prices. We substitute this here by a parameter mu. Mu, actually, where's my cursor here? Mu, this is, this is mu. And then we get the expected log return over the whole period is nu t. The variance is this and this and this. Don't remember this. Don't need to remember this. And if we now all plug this into the geometric Brownian motion, we get this equation here. And it's the exact solution. So the stock price at point t is the original stock price at which we started out times the exponential function of nu t plus sigma and this integral of the Wiener process. And actually, we need to solve this, we need to discretize this, and what we get is the stock price at point t plus delta t is given by the price at st times the exponential function of nu delta t plus sigma square root of delta t epsilon. Slightly different than the Euler scheme, but this has a smaller discretization error. Let's do this in Matlab. Very, very simple. We simulate from the geometric Brownian motion. This function, we call it acid paths. You need to remember this for the following slides because we are going to rely on this function heavily. We start out at S0. We have a parameter mu. We have a parameter sigma. We have a time horizon delta, capital T. And we want to simulate n steps. And we want to simulate n REPL simulations. So REPL stands for replications, and steps is simply the number of steps we are taking. So for example, it could be, so this would be 1, 2, 3, 4, 5, 6, 7 steps. N steps would be 7. And if we do this, hopefully these are 7 steps. Actually, it needs to start at the same point. Okay, so these would be 4 or 5 n steps simulations. Okay, we start out with a vector of zeros. We initialize the first column of our matrix with S0. We all start at S0, the current stock price. dt is the change in time, simply t divided by the number of steps. So for example, it could be 1 year into 365 steps, 365 days. So dt would be 1 over 365. Nu dt, sigma dt is simply calculate nu and sigma times dt and the square root of dt. And then each step is simply the next stock price is given by the previous stock price times the exponential function of nu dt plus sigma dt, psi dt, and rand n. Rand n is epsilon. That's a random number epsilon from a standard normal distribution. So that's why it's random number, of n, the normal distribution in Matlab. Let's do this 3 times. Let's simulate 3 paths, and actually it looks like this. This is geometric Brownian motion, 3 potential simulated paths. They all start out at 50. And as you can see with these parameters, probably in negative drift, let me just see, on a very small drift. And we have 3 potential time evolutions and paths from the geometric Brownian motion. Now what to do with this? Very, very simple. In Monte Carlo simulation, you now do what? If this is a plain vanilla option, for example, you simply take this stock price, this stock price, and this stock price. You enter these into the payout profile. You calculate the option returns that you have. Sorry for that. You have 3 potential underlying prices. You plug them into the payout profile, and then you calculate the option payouts at this point, and you need to discount this to this point. Then you have 3 discounted. Let's say these are the 3 option payouts. You have 3 option payouts, and you need to take the average. You simply calculate the average. Okay, now we will now explain the Monte Carlo simulation in practice in Matlab. And what we are trying to do now is we want to price a so-called European style exchange option on 2 underlines, U and V. The prices of the underlines, they follow a 2-dimensional geometric Brownian motion with DUT and DVT. As you can see, these are geometric Brownian motions if taken for themselves, but they also have a correlation row between them. And the payout profile at the time of maturity is the maximum of VT minus UT and 0. This is a special case of a spread option, as you can see, because you get the spread, if it's positive, between V and U and 0 otherwise. Okay. Now for this kind of an option, we actually have an analytical solution from the Black-Scholes equation. It's a little bit complicated. As you can see, it's V0 and D1 minus U0 times n of D2. D1 and D2 are given by these expressions, and this is where the correlation between the two actually comes into play. You can see we don't take sigma, but we actually take sigma hat, which incorporates the correlation between those 2 processes. Okay, so this is the Black-Scholes solution, the analytical solution. So again, actually, we wouldn't need Monte Carlo simulation. But we'll compare our Monte Carlo simulation result later on with the Black-Scholes result. So let's first code the analytical evaluation, which is the function exchange, gives us the price. As you can see, this is simply, we take sigma hat D1, D2, and the price is V0 norm CDF of D1 minus U0 times norm CDF of D2. Very simple. Now for Monte Carlo simulation, we need to simulate random numbers from a multivariate normal distribution because we want to simulate from a multivariate geometric Brownian motion. So we calculate the following. Epsilon 1 is simply a standard normal distribution, Z1, and epsilon 2 is, well, a second standard normal distribution, but it's connected with epsilon 1 via the correlation. So if you have a correlation of 1, or if you have a correlation of -1 or 0, you can see that actually we have more or less or no dependence between epsilon 1 and epsilon 2. And then, again, we discretize the geometric Brownian motion. We insert epsilon 1 and epsilon 2, and we get simulated paths from the 2-dimensional geometric Brownian motion. Again, at this point, we are not considering a path-dependent option yet. So we need to determine the value of the underlying at maturity at the end. So very simply, this is just similar to this case. Now we have 2 processes, and for each of these 2 underlyings, we need to simulate, let's say, 1,000 or 10,000 simulations. And then you take the, let's say, if we have 3 red lines for V, you would need to take the final values of the blue line and compare them with the corresponding last terminal value of the red line, and then you get the payout of your spread option. So let's do this in Matlab. Function is now exchange MC, V0, U0, sigma V, sigma U, rho, T, R, and N REPL. We simulate from the geometric Brownian motion, multivariate version, epsilon 1, epsilon 2. Then the final value of V and the final value of U are these 2 expressions, simply starting point times exponential function, and so on and so on. And we insert epsilon 1 and epsilon 2. And now we take the maximum of the spread, or 0. We discount it continuously using exponential function minus r times t. And this gives us a vector of discounted payoffs of the option in T0. Now to calculate the option, we could simply now say average mean disk payoff. What we do instead is we fit a normal distribution to a disk payoff, and which does not only give us the mean, the average, but it also gives us a confidence interval around the mean. So this is why we have P, S, and CI. And if we do this with these parameters, you can see the analytical solution from Black-Scholes is 0.8633. We do 200,000 replications, and we do this now using Monte Carlo simulation, and what we can see is the solution via Monte Carlo simulation is 0.8552, very close to the Black-Scholes analytical solution, and the 95% confidence interval starts at 84% and goes to 86%, 86.6%. So as you can see, both the analytical true solution from the Black-Scholes model lies in the confidence interval we've calculated based on Monte Carlo simulation. Now, if you increase NREPL to, let's say, 2 million, what will happen is that this interval will become smaller. So again, at this point, you wouldn't need all this computational effort. For it's interesting to see and quite instructional to see that Monte Carlo simulation, yes, converges with the same assumptions. The only thing that the only thing that is problematic here is that we discretize the geometric Brownian motion. We will always have a discretization error, but all the assumptions we've done are the same for the Black-Scholes model and for the Monte Carlo simulation. But in this case, this is not necessary. We have the analytical solution from the Black-Scholes model, so Monte Carlo simulation is way over the top. Okay. Now, we can also do this for a weakly path-dependent exotic option. That is, we consider a down and out put option. And a down and out put option is a regular plain vanilla put option that becomes inactive, that becomes invalid and worthless if the stock price crosses a downward threshold. For this put option, actually, we also have a pricing formula. The price of a put equals the price of a down and input plus the price of a corresponding down and output. So we have two barrier options, down and in, down and out. If we add them, we get the price of a regular put. Now, again, even though this is weakly path dependent, we again have a Black-Scholes analytical pricing function, and the pricing function is given here. It's not nice. It's an analytical solution, yes, but actually, as you can see, we now need 8 parameters to calculate from our initial ones, and the 1, 2, 3, 4, 5, 6, 7, 8 are given by these expressions. Don't need to remember these, but simply you need to know that a barrier option has an analytical Black-Scholes pricing formula. This is the down and output. We take all these formulas, we code them in Matlab, and as you can see, this gives us the price of a down and output. Okay. Now, we have the analytical evaluation. We price the down and output with a very naive Monte Carlo simulation. Again, we calculate the option payouts, we discount them, and then in the end, we do not simply calculate the average, but we fit a normal function, a normal distribution, to the discounted payouts of the option to not only get the mean, but also get a confidence interval around the mean. Okay, so this is the down and output using Monte Carlo simulation. First of all, we generate asset paths as before, and for each asset path, so for I equal to 1 to n REPL, we take the path and we say crossed is a vector that says if any path is smaller or equal than the barrier. This is a down and output. If the path, if the simulated underlying price goes below the barrier SB, then it's down and out. It becomes invalid. So if crossed is 0 for this asset path, then payoff is a regular put. Else, the payoff is 0 because the put, let's write this next to this, down and out. This is happening in line 12. And we want to know how many times has this happened for, let's say, 10,000 simulations. So n crossed is n cross plus 1. And in the end, we fit our normal distribution to the payoffs discounted, and we get the price and the confidence interval. So let's see what happens. We have the down and output, that's the analytical Black-Scholes price, 1.3629. Down and out Monte Carlo simulation, 1.3597 with 100,000 simulations. You can try this at home and see what happens with only 100, 1,000 or 5,000 simulations. Will be farther away from the Black-Scholes price. And again, the confidence interval, well, you can see the confidence interval includes the Black-Scholes price. So 100,000 simulations are enough to at least get to the Black-Scholes price with 95% confidence level. And out of these 100,000 simulations, n crossed is 14,000, meaning that in 14% of our simulations, the down and output was actually knocked out. Just as an interesting side note. Okay. Now we can also build in correlations into the random samples to improve the Monte Carlo simulation. This is variance reduction and called conditional Monte Carlo simulation. Why do we do this? Well, we still have a relatively large confidence interval, and we want to make this even smaller and improve the quality of our Monte Carlo simulation. So here, in this example, and I'm only showing this for the barrier options, the starting point is the equation down and out equals the price of a regular put minus the price of a down and input. Okay. Now we assume that we divide the term of the option into intervals of length delta t. Then capital T is m days times delta t, and the underlying path is given by S1, S2, S3, and so on. And we now estimate the option price for the down and in using this function here. Again, Monte Carlo simulation. We have to discount the expected value of an indicator function times a regular, that's actually the regular put, right? So the indicator function is 1 if it has been knocked in. This is a knock-in product, down and in. Otherwise, it's 0. Okay, so we take the down and output. And actually, that's the same slide, sorry. Correct this. And now let J star be the time index at which the barrier is crossed for the first time. Now, for the down and input, we do know that actually at the point of time at which the product is knocked in, it is a regular put until the end of maturity. So what, in essence, what we are doing is we are cheating a little bit, because at this point we simulate a path, and at the point at which the product is knocked in, from that point on we take the Black-Scholes price. So this is actually what we do. We take the expectation of the indicator function times the regular put payout, and this is actually the Black-Scholes price from this point on, at which for one simulation the product has been knocked in. This can be capital T. It has never been knocked in. Then simply we get 0. But otherwise, if it's, for example, knocked in on the very first day, it's simply a regular put. So that's why we are cheating a little bit here, because we can simulate for the down and input. And if it has been knocked in, we do know from that point on we can resort to the Black-Scholes model. So that's what we're doing. We simulate a path. We can use the following estimator, indicator function, times the discounted Black-Scholes price, because remember, let's say this is the underlying price, this is the barrier, then actually we can calculate, we can take this price here, calculate the Black-Scholes price at this point, and then we need to discount this to T0. And this is also conditional Monte Carlo simulation. It only differs in the fact that we use the down and input, we simulate the paths, and from that point on, when it has been knocked in for the first time, then we take the analytical Black-Scholes formula, and we only need to do a little bit more discounting. So if we implement this for the conditional Monte Carlo simulation, we generate the effort paths, we look for the time t crossed is the minimum, and we need to find the point at which path is smaller or equal than the barrier. This is the defining line here. This is where we check whether the product has been knocked in. If not, is empty t crossed, then nothing happens. If n crossed is larger than 0, well, then we take the Black-Scholes price. We take the previous function, we get the Black-Scholes price, and then we calculate actually put minus payoff. Remember, we want to do this for a down and output, and we are doing all of this here for a down and input. So we calculate the down and input, we calculate the regular put, and then the down and output is given by norm fit of put minus payoff. Remember this. Okay, so if we do this now, if we take the regular down and out Monte Carlo simulation, we get this confidence interval. If we now do the conditional Monte Carlo simulation, same number of replications, same number of simulations, we get this confidence interval. And as you can see, from 385 to 389, we get to 386, 386. So a considerable decrease in the size of the confidence interval. And why do we and how do we achieve this? Well, by incorporating information that actually a part of the evaluation can be done by the true analytical formula from the Black-Scholes model. Okay, this is the Monte Carlo simulation. Now, next, I want to price an Asian option, an Asian average rate call option. This is the last example of an exotic option. As you can see here, the payoff function of this option is given now by the maximum of the average minus the strike or 0. We can also assume that the prices are measured at equidistant times every day, every closing quote, and we again want to price this using a simple Monte Carlo simulation. Okay. Very simple code. The function is called Asian MC. We have a starting underlying price as 0, then strike, interest rate, maturity. Again, the number of samples we take and the number of replications, and the payoff is first of all a vector of zeros. Then for each simulation we take path, asset path as 0, r sigma t and samples and 1, and then the payoff is what? We simulate the asset path and we take the mean of each simulation run minus the strike or 0, and we get the payoff, and then again take the payoffs, discount them, and fit a normal distribution to it, and we get the Asian option priced. Now, again, we want to improve this a little bit, and we can do so via a very simple approach that adds a control variable. Now, the general procedure for variance reduction using control variables is based on the following idea. Let us assume that we intend to estimate theta, which is the expectation of x. Now let's assume we are given a different variable y that is correlated with x and has expectation nu. Now let's, and we don't know anything else, what the correlation looks like. We only know that y is correlated with x. So we call y a control variable, and then have a look at the control estimator xc equal to x plus c times y minus its expectation. Very interesting to see that the expected value of xc is again theta. So if we calculate the expected value of xc, we again get the parameter theta that we are trying to estimate. But the variance of xc is given by variance of x plus c squared times variance of y plus 2 times c times the covariance between x and y. And if we now take c to be, this parameter c to be c star, defined as minus the covariance divided by the variance, we can see that actually the theta stays the same and the expectation of xc stays the same, it's theta. So it's an unbiased estimator, but actually the variance of xc star divided by the variance of x is 1 minus the squared correlation. So if the correlation is not 0, the variance of xc, the variance of the controlled estimator, will be lower than the variance of the initial estimator x. That's why if you have a correlation for your control variable, choose c star like this, and you get a controlled estimator xc that actually has a smaller variance. So this is very nice. So we need a control variable y that is correlated with our x. X is the option price. In this case, we can use y. So actually, we take the sum of these stock prices, and this should definitely be correlated with x. Now, this option is, or this choice, has the advantage that we can determine the expected value, and y is obviously correlated with the option price. We could also use the price of an average geometric option, but we use the sum, and the expected value of the sum of the underlying prices is y, and if we calculate this, we actually get this expression here. And if we do this in Matlab, it's actually very simple. What we first do is we need to run a simulation as a pilot study. Before that, we do a first simulation. We simulate from the asset paths and calculate our stock sum. This is what we do here. We calculate our y, and then we calculate the variances, covariances between the stock sum and the tryout for the payoffs. We calculate C. This should be C star actually. This is previously our C star, as you can see, minus covariance divided by the variance of stock sum. And then we do our original Monte Carlo simulation, but based on the controlled estimator. So this is what we do here. The control variables, stock path, asset path, payoff, and so on and so on. And in this case, it's the mean of the stock path minus k, and the control vars is payoff x plus c times y minus the expectation of y, which is mu, all based from the previous first simulation. And then we fit a normal distribution to our variable control vars. If we now do this and compare standard Monte Carlo simulation with this Monte Carlo simulation using a control variable, you can see again the confidence interval becomes much, much smaller. The size decreases. Okay, so this is Monte Carlo simulation. Next, as a final method to price an option, we'll have a look at finite differences. What are finite differences? Well, the starting point is again the stochastic partial differential equation from the Black-Scholes model. This is the one you see. We have the Greeks in the partial differential equation, the partial derivatives of the option price f with respect to time and the stock price, and twice the stock price. And we remember that we needed to find suitable boundary conditions for the partial differential equation to solve the PDE. Now, finite differences sounds extremely complicated. It actually isn't. Finite differences are a very simple idea, and I want to show you what we do here. If you remember your math lecture, you might remember that actually taking the integration and derivation, calculating the derivative of a function, are two sides of the same coin. It's connected in calculus via the principal theorem of calculus, the main theorem. And actually, what do you do if you need to calculate an integral? Numerical integration or quadrature is actually quite simple. What you do is, if you need to calculate the space below a function, you use rectangles. Actually, this is how the Riemann integral is defined. It's the limit of those Riemann sums. Integrieren numerisch, wissen Sie, Sie bilden da einfach entsprechend die Riemannschen Flächen und die Riemann-Summen, und die können Sie, wenn Sie wenn Sie die immer weiter verkleinern, dann bekommen Sie ja die Definition gerade des Riemann-Integrals. But what would you do if you needed to, let me delete this. What would you do if you needed to calculate the first derivative? Now, you know, the first derivative at this point is the slope of the tangent to the function. So this here, the slope of this tangent is the value of the first derivative at this point, the red dot. Now, how would you approximate the first derivative for any function if you don't know the first derivative? Let's say you don't know this, you don't know this, you don't know this, but you need those three to solve the partial differential equation. What would you do? Well, very simple. You would take, maybe I will try to zoom in here. Oh, very nice. I've never done this before. Looks okay. Sorry. Magic. So what would you do if you want to calculate this slope? Well, you could, for example, take this point and this point and connect the two and simply use the slope of this line. Not a very good approximation. You could use this point here and this point here and connect these two and use these 2 points. Or you can connect these 2 points, then obviously you add the slope of this line as an approximation. That's what we call a finite difference, basically. Instead of using the differential quotient, we use the difference quotient. Ja, Sie nehmen nicht den Differentialquotienten, die Ableitung, sondern einfach den diskreten Differenzenquotient. Deswegen nennt man das finite Differenzen, endliche Differenzen. So you approximate the first derivative and the second partial derivative and so on by discretizing this and by using finite differences. And you've already seen here 3 potential ways of doing this. You can use this point where you want to approximate the derivative, and a second point to the right, that's called a forward difference. You can use the point and a point to the left, then you have a backward difference. And well, actually, you can already guess, you can take one to the left and one to the right and you get a third type of finite differences. Now, this is what we are doing here. We are solving the partial differential equation by substituting those partial derivatives using finite differences. Finite Differenzen sind, jetzt zumindest hier in unserem Beispiel, simpel bis zum geht nicht mehr. Genauso wie Sie in der Schule schon Integrale einfach durch letztlich Riemannsche Summen und einfach Rechtecke oder Trapeze oder ähnliches unter der Fläche der Funktion approximiert haben, genauso gehen Sie jetzt hier vor. Sie kennen die Ableitung nicht. Das, was Sie einfach machen, ist, Sie ersetzen die Ableitung durch hier einfach Steigungsdreiecke. Sie nehmen zwei Punkte, den in der Mitte und einen rechts, den in der Mitte und einen links oder einen links und einen rechts. Sie bauen dort einfach zwischen diesen Punkten das Steigungsdreieck auf und die Steigung hier dieser Geraden ist dann Ihre Approximation an eine dieser drei partiellen Ableitungen. Und damit können Sie, wenn Sie es einsetzen, letztlich natürlich diese Differenzengleichung sofort lösen. Relativ einfach. That's finite differences. So we need to span a discrete lattice with dimensions, time, and underlying prices. So as you can see, if we have this function, we have x and y. To do this, we need to discretize x. And because this is two-dimensional, we have to discretize t and s. What we will get is, let me just show this, we get t 0, 1, 2, 3, 4, 5, 6, 7, and we get the stock prices 1, 2, 3, 4, 5, 6, 7, 8. We will start at time 0, and this is maturity. We will start at 0 stock price, and it will go up, and we need to do this. We call this simply as max, a maximum stock price. And then we get a lattice. Wir bekommen also ein diskretes Gitter wieder und müssen dann jetzt hier diese Differenzengleichung, diese ursprüngliche partielle Differentialgleichung und so weiter, auf diesem diskreten Gitter lösen. Now, we do know that this partial differential equation is not enough to solve this. We need boundary conditions. Do we know boundary conditions? Well, obviously, we do know the option payout at maturity. Now, that's the payout profile of the option. But if Fs max is the maximum stock price for a put or a call, probably we know the maximum payout or it will all be 0. So we do know this. And for a stock price of 0, we can also immediately calculate the payout. So we can do this as well. We do know these as well. And then basically from these three columns and lines, we can calculate the points here and so on and so on. And we can fill our lattice and then calculate the partial derivatives. So the discrete lattice consists of S, starting out with S0, going up to S max, and then T starts at 0 and it goes up to capital T. The individual values of our function Fij, the option price, the derivative price, is simply Fij. We abbreviate this and say this is Fij. This is the option price for the ith stock price and the jth time interval. Now, I said we have three different ways of using differences. Forward difference, one to the right, and Fij. Backward difference, Fij, and one to the left. And central symmetric difference is one to the right and one to the left and one to the right. Same for the partial derivative with respect to S and T. So these are 1, 2, 3, 4, 5, 6, three ways of writing down the partial derivatives. We also need the second partial derivative in the Black-Scholes formula, and this one can be approximated also with a forward difference, as given here. And now we only need to insert these partial derivatives, these approximations to the Greeks, into our lattice. And again, we need the boundary conditions. For a plain vanilla put, we do know the nth column, the first line and the upmost line. For the European plain vanilla call, same thing, only with a different payout profile. Okay, now let's first implement the solution for the PDE and a European vanilla put. We approximate the partial derivatives to S using central or centered or symmetric differences, and the derivatives to T using backward differences. And as a result, this is only inserting these formulas into the partial differential equation here. Greek plus RS Greek plus 1/2 volatility S squared, and you can see this is exactly this. We substituted all these partial derivatives using centered and backward differences. And we also have the boundary conditions. Now what we do is, again, we always do this, we go back in time. We have this column, and then we fill this, and this, and this, and this, and this column. And then we have all potential option prices for any starting point. And if we, for example, know that this here is S0, then that's the option price. If the the underlying price is between here, we need to interpolate. So for example, if this is an option price of 5 and this is 7, well, then we would say, okay, the option price is somewhere in between. If we interpolate, probably 6. Okay. Now, we go back in time. We rewrite this equation. It takes a lot of time to arrange all these formulas. And what we get is Fij minus 1. That is the ith value in the previous column. J is the column. So this is J minus 1 is AI star Fi minus 1 J, J, and J. So actually what we are doing is we need this point, and this point. They all three enter this point here. And then we have AI star, BJ star, and CJ star, and these are given by these. A lot of formulas, not very complicated, but it takes a lot of time to implement it in Matlab. So this is the Matlab function using an explicit scheme. So M, ds, n, dt. We set up the lattice, that's vet s, vet I, vet j in the matval. We set up the boundary conditions, so actually in the first column, first line, last column, last line, we know these three in the matrix. We set up the coefficients a, b, and c. That's actually this here. And we solve it backward in time. That's the recursion. And then again, remember that it might be that the first stock price S0 is right between 2 points of the grid, so we need to interpolate that. And if we now do this, the Black-Scholes price in this case is 4.0761. If we use an explicit scheme, we get a price of 4.0669, close to the Black-Scholes price. Slightly different option, again 2.8446, 2.8288, same thing here. And a third example, Black-Scholes price, actually, no, that's actually the same one here, but slightly different parameters. You suddenly see that the price explodes. Well, this is not without potential errors. And in this case, actually, the approximation using finite differences in some cases can be numerically unstable. And one way to avoid this is to use an implicit scheme. And we now use forward differences for this. We get a slightly different lattice. This is again, as you can see, this is the PDE. This is a partial differential equation where we've substituted the Greeks using forward finite differences. We get an even more complicated scheme. We have some unknowns A1, AI, BI, and CI. Actually, you don't need to remember this. This is simply a variant of the explicit scheme. It is more computational effort because you now need to solve this system of linear equations. Because it's sparse, it can be accelerated. Actually, have a look at the Matlab code and you can try to understand each line at home. Again, we need to set up the lattice. Wir müssen erstmal das Gitter aufspannen und dann auch befüllen. Die boundary conditions einbauen. We have to set up the boundary conditions. Again, first line, last column. And then we have to set up this tri-diagonal coefficient matrix with A, B, and the coefficient matrix looks like this. This is actually this one here. And then we need to solve the system of linear equations. This is done here. This is the operator in Matlab to solve a system of linear equations. Damit können Sie ein Gleichungssystem, lineares Gleichungssystem in Matlab lösen. And then we get our values in the first column. Remember, this is what we are looking for. We are interested in these values because these are the values f I1, and those are all the potential option prices, and we need to see, is our stock price here or is it here? If we interpolate, and then we get our solution for the option price. Okay, so you've now seen many different types of methods, many different methods for pricing options and derivatives. We have Black-Scholes, the perfect choice for plain vanilla options every time we have an analytical pricing formula. We then have Monte Carlo simulation, rather a brute force approach. Use computer power, simulate from your asset paths, from your asset model, and put it into the payout of the option. Can be done for any option, but it only makes sense for exotic options when you don't have an analytical solution to the Black-Scholes formula. And you can also use the binomial model, the trinomial model. The binomial model is basically the discretization of the Black-Scholes model, and in this sense the Black-Scholes model is the limiting case if you were to use an infinite number of time intervals. And last but not least, you take the partial differential equation and you insert finite differences instead. You approximate the derivatives using finite differences. That's option pricing in a nutshell. Now, what to do with this? Very simple. You can use options. If you add options to existing long or short positions, you can hedge those positions. You can hedge your position by adding a derivative, and you can also speculate on certain time or certain expected evolutions of your price, and then you have a hedging strategy. You have a hedging strategy for selected risk types, and this is what we'll discuss next week in probably what will be our last lecture. Okay, so we'll stop here for today, and if you have any questions, please stay in the Zoom room, and then we can discuss your questions. Thank you.